With the release of new images from the new James Webb Space Telescope, many of us must have been wondering just how advanced the $13 billion telescope is. How far can it see? How do these observations compare to Hubble's? Let's compare these two telescopes and see which one is better. The Space Shuttle Discovery launched the Hubble Space Telescope into Earth orbit. It was launched in 1990 and remains one of the world's most versatile telescopes. Since then, Hubble has created spectacular images that have not only inspired and moved us to tears, but have also provided invaluable scientific insight, demonstrating that the rate of expansion of the universe is actually accelerating due to some mysterious force known as dark energy. The James Webb Space Telescope, JWST, was launched on December 25, 2021. Hubble is estimated to cost around $16 billion by NASA. James Webb, on the other hand, cost NASA about $10 million to build over a 20-year period. Hubble is still an amazing astronomical tool that will continue to do science for years to come, but scientists wanted more, which is why the James Webb Space Telescope was developed. Webb is Hubble's scientific successor. Its scientific goals were inspired by Hubble's observations. Hubble's science pushed us to look to longer wavelengths in order to exceed what Hubble had already accomplished. More distant objects in particular are more strongly redshifted, and their light is pushed from the UV and optical into the near-infrared. Observing these distant objects, such as the first galaxies formed in the universe, requires the use of an infrared telescope. Webb is not a replacement for Hubble because its capabilities are not identical. Webb studies the universe primarily in the infrared, whereas Hubble studies it primarily in the optical and ultraviolet wavelengths, though it has some infrared capability. Webb's mirror is also much larger than Hubble's. JWST's primary mirror consists of 18 hexagonal mirror segments that are gold-plated. Webb has a primary mirror that is approximately 6.5 meters in diameter, giving it a significantly larger collecting area than the mirrors available on the current generation of space telescopes. Hubble's mirror has a much smaller diameter of 2.4 meters and a collecting area of 4.5 square meters, giving Webb approximately 6.25 times more collecting area. Because Webb has a larger light collecting area, it can see further back in time than Hubble. There is no other instrument other than the JWST that can see the very first galaxies form in the universe. Hubble will be 1.5 million kilometers away at the second log-range L2 point. While Webb will be in a very close orbit around Earth, Webb's solar shield will block light from the Sun, Earth, and Moon at the L2 point. This will keep Webb cool, which is critical for infrared telescopes. Webb will not orbit the Earth, but will remain fixed in the same position in relation to the Earth and the Sun. Satellites orbit around the L2 point. They do not remain completely motionless at a fixed point. In terms of Webb length, Webb primarily observes in the infrared and will be equipped with 4 science instruments: the origins of light in the universe, the formation of galaxies in the early universe, the birth of stars and protoplanetary systems, and planets, including the origins of life to capture images and spectra of astronomical objects. The wavelength range covered by these instruments will be 0.6 to 28 micrometers. The infrared region of the electromagnetic spectrum ranges from 0.75 to a few hundred microns. This means that Webb's instruments primarily operate in the infrared region of the electromagnetic spectrum, with some capability in the visible region. Hubble's instruments can observe a small portion of the infrared spectrum from 0.8 to 2.5 microns. But its primary capabilities are in the ultraviolet and visible ranges from 0.1 to 0.8 microns. Why are infrared observations important in astronomy? Stars and planets in the early stages of formation are hidden behind dust cocoons that absorb visible light. The same is true for our galaxy's nucleus. Infrared light emitted by these regions, on the other hand, can penetrate this dusty shroud and reveal what is inside. Have you ever wondered, how far will Webb see? Because of the time it takes light to travel, the farther away an object is, the farther back in time we are looking. The illustration compares different telescopes and how far back they can see. Essentially, Hubble can see toddler galaxies, while Webb telescope will be able to see baby galaxies. Because Webb is an infrared telescope, it will be able to see the first galaxies. The universe and thus its galaxies are expanding. When discussing the most distant objects, Einstein's general relativity comes into play. It tells us that as the universe expands, the space between objects stretches, causing galaxies to move away from each other. Furthermore, any light in the space will stretch, causing its wavelength to shift to longer wavelengths. Because infrared light reaches us, this can make distant objects appear very dim or even invisible at visible wavelengths of light. Webb infrared telescopes are ideal for observing these early galaxies. James Webb is also capable of detecting faint chemical signatures in exoplanet light. In the coming months, Webb will point its telescope at TRAPPIST-1e, a potentially habitable Earth-sized planet 39 light-years away. Webb can search for biosignatures by watching planets pass in front of their host stars. It has the ability to capture starlight that has passed through the planet's atmosphere. But Webb's goal was not to find life. As a result, the telescope can only examine a few of the nearest potentially habitable worlds. It can also detect changes in carbon dioxide, methane, and water vapor levels in the atmosphere. While certain combinations of these gases may indicate the presence of life, till now, Webb is unable to detect the presence of unbonded oxygen, which is the strongest indicator of life. On July 11, 2022, NASA released the first of a series of images captured by the new James Webb Space Telescope. The new image provided an unprecedented look into deep space and was a significant improvement over similar images captured by the Hubble Space Telescope's predecessor. It was captured using near-infrared sensors, which capture a different spectrum than a standard camera. JWST is faster than Hubble and produces better results. Hubble took weeks to scan its image of deep space, whereas JWST did so in 12 hours and 30 minutes. The comparison becomes even clearer when you zoom in. The images showed here compare Hubble and JWST renderings of the SMACS's 0723. Hubble and JWST renderings of SMACS's 0723, a cluster of galaxies that appeared around 4.6 billion years ago. When we look back to when the universe was only a fraction of its current age, the ultraviolet and optical emission from the earliest galaxies shifts into the infrared, to wavelengths that Hubble cannot see but that Webb is perfectly suited to measure. The powerful James Webb Space Telescope, like its predecessor, the Hubble Space Telescope, is expected to take amazing photos of galaxies in the future. This brings us to the end of the video. Both of these telescopes are excellent in their own places. Hubble was the first to begin, providing us with various images of our galaxy. And now James Webb is providing us with more detailed images of our galaxy. It will do even more in the future.